Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine for a second you're just looking up at the night sky, right?
Right, just taking it in.
Yeah. And you're watching one of the absolute brightest street lights in the entire universe simply turn off.
Just completely go dark.
Exactly. And I don't mean fading away over millions of years as the cosmos slowly ages. I mean, we are talking about a beacon so luminous that it outshines entire galaxies.
Oh, easily.
And it dims so incredibly fast that you actually witness it happen within a fraction of your own lifetime.
It really is a staggering image. And I think it fundamentally breaks how we are taught to perceive the cosmos.
Right.
Because we're basically conditioned to view the universe as this static painting.
Yeah, like it's unchanging.
Exactly. We just assume that astronomical changes happen on these massive timescales that render a single human life practically invisible.
A blink of an eye.
Right. But the event we're dissecting today, it proves that assumption completely, undeniably wrong.
And that is exactly our mission today. We are taking a journey roughly 10 billion light years across the universe to explore a cosmic anomaly that is, frankly, forcing astrophysicists to rewrite the entire rulebook.
Yeah, they really are.
We are investigating the sudden, dramatic, and honestly pretty violent dimming of a very distant galaxy.
Violent is definitely the right word for it.
And by the time we're done here, you'll understand the intricate machinery that powers the brightest objects in the cosmos.
Which is fascinating in itself.
Oh, absolutely. Plus, you'll see how astronomical cold case detectives essentially use 70-year-old evidence to solve modern mysteries.
I love that part of the story.
It's so good. And we'll get into why everything we thought we knew about the lifespan of supermassive black holes might just need to be thrown right out the window.
Yeah, because to really appreciate the shockwave this sent through the astrophysics community, we first have to establish the scene of the cosmic crime, so to speak.
Right. Let's set the stage. Where are we looking?
So the focus is this specific, incredibly distant galaxy. It's cataloged as J0218-00386.
Catchy name.
Very catchy, right? Standard astronomical naming. But astronomers measure the distance to these far-off objects using a metric called redshift.
Okay.
And J0218 has a redshift of 1.8.
Let's actually break down what a redshift of 1.8 actually means because, it's not just a physical distance.
Right, it's not just miles or kilometers.
No, it's a temporal distance. It's time. Because light takes time to travel, looking across space is quite literally looking back in time.
Cosmic time machine.
Exactly. It's like receiving a postcard in the mail that took 10 billion years to arrive.
That's a great way to put it.
And the unsettling part is, as you're holding this ancient postcard in your hands, the picture on the front drastically fades right before your eyes.
Yeah, that temporal aspect is so vital to understand, because when we observe the light from J0218, we are seeing the universe as it was when it was only roughly a third of its current age.
Wow, only a third.
Yeah. This era, around a redshift of 2, astronomers often refer to it as cosmic noon.
Cosmic noon? That sounds intense.
It was. It was this period of intense, rapid star formation. Galaxies were incredibly active, chaotic, constantly colliding and merging.
So finding a tremendously bright object in that specific era isn't really the surprise, right?
Not at all.
Yeah.
We expect things to be bright and violent back then. The shock came when an international team led by Tomoki Morikuma at the Chiba Institute of Technology, when they discovered that the brightness of J0208 suddenly plummeted to just 1/20th of its original level.
1/20th.
And the craziest part, it did this in merely 20 Earth years.
See, a 20-fold drop, that means we are looking at a system that went from operating at peak luminosity down to just 5% of its previous output.
5%.
If you're, say, driving to work right now, think about the engine in your car.
Okay.
If your engine suddenly lost 95% of its power, you wouldn't just call it a minor fluctuation.
No, you'd pull over immediately.
Right. You would assume a catastrophic mechanical failure.
That is a highly accurate way to frame it, actually. Because an object visible from 10 billion light years away is generating energy on a scale that completely defies everyday comprehension.
It's unfathomable.
Truly. So to lose 95% of that massive energy output in just 2 decades, It signals a complete systemic breakdown of the engine driving that light.
Which brings us to the mechanics of the engine itself. Because a 20-fold drop in brightness is massive, but to grasp the true scale of what was lost, we really need to understand what was generating all that light in the first place.
Right. What's the fuel? What's the engine?
Yeah, because we aren't just talking about a really big cluster of stars here.
No, definitely not.
We are talking about an active galactic nucleus, or an AGN.
Yeah. So if we look at the anatomy of most large galaxies, including our own, actually, we find a supermassive black hole right at the core.
And when we say supermassive,
we are talking about an object with a mass of hundreds of millions, sometimes billions, of times the mass of our own sun.
Just compacted into a tiny point.
Exactly, compacted into a relatively tiny region of space. Now, in a quiet galaxy, like our Milky Way, the black hole is mostly dormant.
Right, it's just sitting there.
Yeah, it's fasting. But in an active galactic nucleus, the environment is violently chaotic. You have these immense clouds of gas and dust constantly being pulled inward by the black hole's gravity.
But wait, knowing the engine is powered by a black hole makes this whole scenario sound incredibly counterintuitive to me.
How so?
Well, we all know the fundamental rule of astrophysics, right? Nothing escapes the event horizon.
Right. Not even light.
Exactly. Black holes are the ultimate cosmic vacuum cleaners. They trap light. So how is it that the area immediately surrounding the darkest object in the universe somehow becomes the brightest thing we can possibly see?
It is honestly one of the most beautiful paradoxes in physics.
I mean, is it purely just the friction of some cosmic traffic jam?
That's a huge part of it. The key is really differentiating the black hole itself from its surrounding environment.
Okay, separate the hole from the waiting room.
Exactly. The event horizon is the boundary of no return. But the light we see from an AGN isn't coming from inside the black hole.
Obviously not, because we wouldn't see it.
Right. It's coming from the accretion disk. That is the waiting room of material just outside the event horizon.
So what's happening in that waiting room?
Well, as gas is pulled inward, conservation of angular momentum forces it to swirl around the black hole.
Kind of like water circling a drain?
Exactly like that.
Right.
And it flattens out into this vast, incredibly dense whirlpool of plasma.
And as that plasma spirals closer and closer to the event horizon, it accelerates.
Massively. The inner tracks of this whirlpool are spinning at a significant fraction of the speed of light.
Wow.
Meanwhile, the outer tracks are moving much, much slower.
Ah, okay. So the inner lanes of the highway are moving at near light speed, and the outer lanes are sluggish.
Yes. And that differential rotation creates something we rarely associate with the vacuum of space, which is profound friction.
Because things are rubbing together.
But it's not the simple mechanical friction of two solid objects rubbing together, like rubbing your hands to get warm.
Right, because it's gas.
Well, it's plasma. They're dealing with plasma physics here. So the friction is actually driven by magnetic fields threading through this ionized gas.
Oh, interesting.
Yeah. As these layers of plasma shear against each other at relativistic speeds, it triggers a phenomenon called magnetorotational instability.
Magnetorotational instability. That sounds like a mouthful.
It is. But basically, it just creates immense, violent turbulence within the disk.
Okay.
And that turbulence is what converts the gravitational potential energy of the infalling gas into staggering amounts of heat.
So we aren't just talking about the gas getting a little warm.
No. The friction generated by these magnetic turbulent forces heats the plasma to hundreds of thousands, sometimes millions of degrees.
Millions of degrees. That is insane.
And at those extreme temperatures, the gas glows brilliantly across the entire electromagnetic spectrum.
So it's basically screaming as it falls in?
Exactly. It's the death cry of the gas just before it crosses the event horizon. And the efficiency of this process is difficult to overstate.
How efficient is it compared to, say, a star?
It's wildly more efficient. Dropping mass into a supermassive black hole via an accretion disk is actually one of the most efficient ways to generate energy in the known universe.
Wait, really? More than fusion?
Far more efficient than the nuclear fusion powering stars like our sun.
I had no idea.
Yeah, that is exactly why a single AGN can outshine hundreds of billions of stars combined.
Okay, so we have established this blindingly bright vortex of superheated plasma, fueled by the immense gravity of a monster black hole.
Yes.
Pumping out more energy than entire galaxies.
That's the engine.
But knowing that the engine is a massive accretion disk makes this rapid shutdown even more impossible to believe.
It really does.
Because we are talking about physical structures that are light years across, right?
Sometimes, yes. They are immense.
So the inertia alone means an engine that massive physically cannot stop that fast. You can't hit the brakes on something light years wide and expect it to halt in 20 years.
And that right there is the 20-year glitch.
Yeah.
That is exactly where standard physics breaks down in this case.
Okay, so let's dig into that glitch. What is the normal behavior supposed to be?
To understand the anomaly, we have to establish that baseline of normal behavior. Active galactic nuclei do vary in brightness. That is known.
Right, they aren't perfectly steady.
Because the flow of gas into the disk is turbulent and clumpy. It's not a perfectly smooth stream. Because of this, it is completely standard for an AGN to vary in its luminous output by about 30% over months or even years.
Okay, so a 30% variation. That makes sense to me. That's like a flickering light bulb on your front porch.
Right.
Sometimes the current wavers a bit, the filament cools for a microsecond, and it dims, then it brightens again.
A perfect analogy. That's just the normal breathing of the accretion disk.
But dropping to 5% of its original brightness, dropping by a factor of 20.
Yeah, that's different.
That is not a flicker. That's someone walking over and violently ripping the power cable right out of the wall.
Exactly. And when astrophysicists build models to describe the physics of these accretion disks, they deal with very specific mathematical timescales.
What kind of timescales?
Well, there is the dynamical timescale, which dictates how fast things orbit the black hole.
Okay.
But more importantly for this mystery, there is the viscous timescale.
Viscous, like viscosity, like honey.
Exactly. It's the time it takes for mass to actually flow through the friction of the disk and eventually fall into the black hole.
Ah, I see.
And for a supermassive black hole, the viscous timescale is immense. Changes in the fundamental mass accretion rate, the actual fueling of the black hole, should happen incredibly slowly.
How slowly?
Over tens of thousands of years at the absolute minimum.
So, meaning, if you hypothetically cut off the fuel supply at the outer edge of the disk today,
Yes.
it should still take tens of thousands of years for the inner part of the disk to finally drain out and go dark.
Yes. The math simply does not allow an object containing hundreds of millions of solar masses to shut down its primary energy generation in 20 years.
It's just too fast.
Way too fast. To put it in geological terms, down here on Earth, it is equivalent to watching the entire Himalayan mountain range completely level out into a flat plain overnight.
Wow.
Just wake up and the mountains are gone.
And if a geologist saw the Himalayas flatten overnight, their first instinct would be to assume their equipment was broken.
Exactly. You check your sensors.
Right. You can't just claim you broke standard physics without bringing absolute ironclad receipts.
And these researchers knew that.
So to prove this wasn't just some instrument error, astronomers had to pull together an unprecedented multi-generational investigation.
And the methodology they used is just a masterclass in observational astronomy.
Let's walk through that detective work, because it's fascinating.
It really is. The discovery wasn't a sudden eureka moment at a telescope eyepiece where someone gasped, you know.
Right. It's not like in the movies.
No, it relied on comparing immense digital data sets that were separated by nearly 2 decades and then corroborating all of that with historical archives.
Okay, so where does the timeline start?
The before picture, the baseline of this roaring bright AGN, was established around 2002 by the Sloan Digital Sky Survey.
Okay, the SDSS, that's pretty legendary in astronomy circles, right?
Oh, absolutely. It wasn't just looking at individual objects. It essentially created one of the first highly detailed, massive 3D maps of the observable universe.
Just scanning massive swaths of the sky night after night.
Exactly. And it provided a vital benchmark for what the sky looked like at the turn of the millennium.
Right. But obviously, astronomy technology evolves incredibly rapidly.
It does. Fast forward to 2018, and researchers were using the Hypersa Prime Cam.
The HSC.
Right, mounted on the Subaru telescope in Hawaii. The HSC uses these highly advanced charge-coupled devices that are far, far more sensitive than what was available back in 2002.
So they get a much crisper look.
Exactly. So this international collaboration, which, by the way, required coordinating massive teams across Japan, Germany, and Spain, just to process the sheer volume of data.
Just moving the hard drives must have been a nightmare.
Seriously. But when they compared the 2018 HSC images to the 2002 SDSS data, The discrepancy in J0218 was glaring.
The light had simply vanished.
It's just gone.
But seeing a discrepancy between two digital surveys is, it's a great start, but it's not enough to rewrite the textbook.
Not even close. You need confirmation.
Right. So they launched this massive follow-up campaign.
They threw everything they had at it.
They brought in the Gran Telescopio Canarias. They brought in the WM Keck Observatory for new optical and near-infrared observations.
Yeah.
They pulled in X-ray data. They pulled in radio wave data.
All across the spectrum.
And then, my absolute favorite part, they went into the physical vaults.
Yes. The archival sleuthing.
Scientists literally pulled out physical photographic plates taken roughly 70 years ago to build a complete historical timeline of this galaxy.
It really is a stunning validation of the importance of preserving archival data.
I mean, 70 years ago, we are talking about chemical emulsions.
Long before digital sensors ever existed.
Right.
But those old plates allowed the team to confirm that this sudden dimming wasn't just a return to some historical norm.
Oh, okay.
It allowed them to track the long-term behavior of the AGN over decades and definitively confirmed that the 20-year drop was a genuine, unprecedented anomaly in the object's history.
Okay, hold on. I have to push back on the methodology here for a second.
Sure, go for it.
I love the idea of modern astronomers dusting off 70-year-old physical plates. But you're telling me a piece of glass coated in chemicals from the 1950s is being used to verify a 10-billion-year-old cosmic anomaly?
That is exactly what I'm telling you.
But how do we know the emulsion on those plates hasn't just degraded over the decades? How can we trust an old piece of glass sitting in a drawer to rewrite modern astrophysics?
It is a very valid skepticism, and it's something astronomers actively account for through rigorous calibration.
Okay, how do they calibrate a 70-year-old photo?
Well, you don't just look at the single galaxy on the glass plate in isolation. You look at the entire field of view captured on that piece of glass.
Okay.
You measure the brightness of J0218 against the brightness of dozens of steady, non-variable stars that were captured on that exact same photographic plate.
Oh, I see.
Right. So if the chemical emulsion simply degraded over time, the reference stars would also look dimmer to us now.
That is brilliant.
By measuring the relative brightness between the galaxy and those steady stars, the chemical degradation of the physical plate is completely factored out of the equation.
Okay, that makes perfect sense. The steady stars act as an internal control group for the plate's physical condition.
Exactly. It's very clever.
It is. But let's look at the modern follow-up data they gathered, because I have another question there.
Shoot.
Why did they need radio, X-ray, and optical data? I mean, if the light went out, shouldn't a regular standard visible light telescope be enough to tell us that? Why throw the entire electromagnetic spectrum of the problem?
Because different wavelengths of light reveal entirely different physical mechanisms within the AGN itself.
Okay, explain that.
If you only look at visible light, the optical stuff, you miss the vast majority of the actual physics going on.
Yeah.
An active galactic nucleus is a complex, layered ecosystem.
It's not just one glowing ball.
No, it is governed by extreme thermal gradients.
Yeah.
So the inner region, right next to the black hole, is the hottest part.
Right, where the friction is craziest.
Yeah, exactly. Because it's so hot, it produces high-energy, short-wavelength X-rays.
So it's kind of like the blue flame on a blowtorch being hotter than the yellow flame on a candle?
That is a fantastic parallel, yes.
Okay.
Then the swirling gas further out from the center is slightly cooler, relatively speaking, so that produces your optical and ultraviolet light.
So that's the yellow flame.
Right. And then, even further away from the black hole, you have this massive torus. Essentially a giant donut shape of cosmic dust.
A dust donut.
A dust donut. And that dust actually absorbs the inner light and re-radiates it as long-wavelength infrared heat.
Oh, wow. So you have X-rays in the middle, optical in the middle ring, and infrared on the outer edge.
Precisely. So by looking at all these different wavelengths, researchers aren't just checking to see if the object as a whole got darker.
They are diagnosing which specific parts of the engine broke down.
Exactly. They're checking the spark plugs, the fuel line, everything.
And more importantly, using those different wavelengths was the only way to rule out the absolute most common suspect in astronomical mysteries.
Which is cosmic dust.
Exactly. Because whenever something gets unexpectedly dim in space, it feels like the first instinct is always, did a giant cloud of dust just float in front of it?
It is the most logical assumption based on Occam's razor. I mean, space is incredibly dusty.
Right.
Galaxies are filled with these immense sweeping clouds of silicates and carbonaceous grains that were forged in the depths of older stars.
It's very crowded.
Very. So the most obvious answer to the question, why did the light suddenly get dark, is simply something got in the way.
The hypothesis being that a dense cloud of interstellar dust basically just drifted across our line of sight.
Right. Interposing itself between our telescopes on Earth and the accretion disk 10 billion light years away.
And if that happened, it's not like the projector broke. It's like someone just walked in front of the projector blocking the movie.
Yes. The engine itself would still be chugging along perfectly fine. It would just be hidden behind a curtain of dust.
But they proved it wasn't dust.
They absolutely did.
So how does looking at different wavelengths dismantle the dust cloud theory?
It comes down to the physics of scattering.
Scattering.
Specifically how the physical size of a light wavelength interacts with the physical size of a dust particle.
Okay, break that down for me.
Cosmic dust particles are incredibly tiny, and visible optical light has very short wavelengths.
Right.
When those short, tightly packed wavelengths hit the tiny dust particles, they scatter.
Like hitting a wall.
Exactly. The light bounces off in different directions, and it never reaches our telescopes. That's why dust blocks visible light so well.
But infrared light behaves differently.
Completely differently. Infrared light has a much, much longer wavelength.
Okay.
Because the waves are physically longer than the dust particles themselves, they don't scatter efficiently. The infrared light essentially bypasses the dust entirely.
It just pierces straight through.
Yes. It pierces right through dense clouds that would completely block visible light.
Let's try to ground this with an analogy because I want to make sure I'm visualizing this right.
Go for it.
It's like standing on a pier looking at the ocean.
Okay.
The massive long ocean swells. Those would represent the infrared waves. They roll right past the wooden pilings of the pier like they aren't even there.
Yes.
But the tiny choppy ripples on the surface representing the short optical wavelengths, those smash into the wood and scatter in all directions.
That perfectly captures the physics of wavelength-dependent scattering. I love that.
Okay, so applying that to the galaxy.
Right. If a dust cloud had just drifted in front of JO218, the short wavelength visible light would have crashed into the dust and scattered.
Which would cause a massive drop in the optical brightness we see on Earth.
Exactly. But the long wavelength infrared light, which is pouring out of that hot, dusty torus surrounding the AGN, that should have rolled right past the obstruction.
So the infrared should have remained relatively steady in our observations.
It should have, if it was just dust.
But when the researchers actually analyzed the data across the spectrum, they found that both the optical light and the infrared light dropped dramatically at the exact same time.
And that synchronized drop completely destroys the dust cloud hypothesis.
Because dust can't block infrared.
Exactly. A physical dust obstruction cannot hide the infrared signature of an active accretion disk. Because the infrared light vanished alongside the optical light, the scientists were backed into a corner.
They were left with only one terrifyingly fast conclusion regarding the physical state of the galaxy.
Right. The engine didn't get covered up.
The engine starved.
Yes. The fuel shut down. We shift from a mystery of missing light to a fundamental breakdown of cosmic mechanics.
So what did the data tell them about the fuel supply?
By feeding these simultaneous multi-wavelength drops into complex theoretical models, the researchers determined that the mass accretion rate, the actual physical flow of plasma falling into the black hole, plummeted.
How far down?
It dropped to about 1/50th of its previous level.
1/50th?
Yeah.
So it essentially dropped to 2% of its original fuel intake.
It's fused fumes.
And the most shocking part here has to be the timeline. This starvation didn't take tens of thousands of years, like that viscous timescale math suggests it should.
No, it didn't.
It happened in a mere 7 years.
7 years, which is an infinitesimally small fraction of time in astrophysics.
Right. I mean, 7 years, that's less time than it takes to get a medical degree.
It really is.
And to go from a roaring, galaxy-illuminating cosmic furnace to sheer starvation mode in just 7 years.
It indicates a catastrophic, instantaneous phase change in the accretion disk's physical structure.
But if the fuel supply just vanished, where did all that mass go? I mean, we're talking about a vortex of superheated plasma, likely millions of times more massive than the Earth. It can't just disappear.
And that is the lingering million-dollar question keeping theoretical physicists awake at night.
I bet.
Because we know an accretion disk is maintained by a delicate balance of extreme forces.
What forces?
Well, the immense gravity of the supermassive black hole is constantly trying to crush all that gas inward.
Right.
But the incredible heat generated by the friction creates intense radiation pressure. and that radiation pressure is pushing outward. So the disk exists in this fragile balance between gravity pulling in and light pushing out. It's a concept closely related to the Eddington limit.
Okay, so if the fuel supply drops to 1/50th, that delicate balance collapses.
Instantly.
The outward radiation pressure basically dies.
Exactly. And exactly what happens next is heavily debated in the field right now.
What are the main theories?
One major theory is that the disk might transition into what physicists call a radiatively inefficient accretion flow, or a RIAF.
The RIAF.
Yeah. In this state, the plasma basically becomes so diffuse that it can no longer cool itself efficiently by emitting light.
Okay, so it stops glowing.
Right. The energy gets trapped as thermal heat, and the disk puffs up into a faint, practically invisible sphere of gas rather than a brilliant, glowing whirlpool.
But what triggers that drop in the fuel in the first place? How do you lose the flow so quickly?
That's the real mystery.
Because it can't be like pulling a plug in a bathtub. That implies gravity just smoothly drains the water. But we are talking about plasma moving at relativistic speeds.
Right. A better way to visualize it is imagine a massive high-speed highway where suddenly the structural integrity of the bridge just completely fails.
It crumbles.
Yeah, the plasma is being held in its orbit by magnetic fields and angular momentum. So one theory is a massive magnetic anomaly.
Like what?
Like a sudden inversion or snapping of the magnetic field lines. This could instantly strip the inner regions of the disk of all their angular momentum.
And without angular momentum keeping it in orbit, essentially spinning around, the plasma has nothing fighting gravity anymore.
The structural support vanishes, and a massive chunk of the inner disk simply plunges into the event horizon almost instantaneously.
Wow.
Leaving an empty, starved cavity behind.
That is terrifying.
It gets wilder. Another theory suggests the exact opposite extreme.
Which is?
That the energy generated by the accretion process briefly surged, creating these powerful, magnetically driven winds.
Winds in space.
Cosmic winds. And these winds were so intense, they literally blew the inner region of the disk apart.
Just blasted it away.
Exactly. Sweeping the gas outward and completely severing the fuel line to the black hole.
I mean, both of those scenarios sound incredibly violent.
They are exceedingly violent. But the truth is, the specific mechanism capable of causing a gas supply of this magnitude to shut off in 7 years remains a theoretical ghost.
We just don't know.
We have observed the undeniable aftermath. The lights are off, but the physical catalyst is still hiding in the dark.
And the fact that our current standard models cannot explain how a supermassive black hole goes on a sudden starvation diet in 7 years, it's forcing a complete rethink of cosmic evolution, isn't it?
Oh, absolutely. This discovery isn't just a quirky footnote in some journal. It is actively rewriting the future of astrophysics.
Because it upends that universally accepted view of slow, gradual AGN evolution.
Completely. One of the co-authors of the study, Toshihiro Kawaguchi, pointed out that this rapid variability simply cannot be explained by standard models.
Our mathematics literally do not account for a massive accretion disk draining in under a decade.
No, the math says it's impossible.
I imagine that for a theoretical physicist, though, having your standard models break is actually a really thrilling moment.
Oh, it's the best day of your life.
Right. It means there's an entirely new layer of physics waiting to be discovered.
Science advances when we find the anomaly. When we find the thing that shouldn't exist but undeniably does.
And J0219 is that anomaly.
Exactly. It now serves as a vital test case. Theoretical physicists have a new goalpost.
What's the goalpost?
They must design a mathematical model of an accretion disk that actually allows for a catastrophic structural failure in 7 years without violating the fundamental laws of thermodynamics.
Which is going to be incredibly difficult.
It's a huge challenge.
It's like geology assuming all mountains erode slowly over millions of years, right?
Right.
And then setting up a camera and watching one specific mountain just completely flatten out on a Tuesday afternoon.
Yes.
We don't just quit science and throw our hands up. We realize we need completely new physics to explain the Tuesday mountain.
I love that. The Tuesday mountain. And the search for more of these Tuesday mountains is already defining the next era of observational astronomy.
Because we have to find out if this is a one-off freak accident or a pattern.
Exactly. Tomoki Murakuma, who led the study, he really emphasized the critical shift happening right now with wide-field surveys.
Right. The way we look at the sky is changing.
It is. For centuries, astronomy was basically about pointing a telescope at one specific tiny keyhole in the sky and studying it deeply.
Right, looking at one star or one galaxy for hours.
But the problem is, You remain completely blind to the 99.9% of the sky you aren't looking at.
But with new tools like the Hypersuprime Cam and all these upcoming facilities that are designed to map the entire sky every few nights,
we are shifting from taking static Polaroids to basically recording a continuous dynamic movie of the universe.
which is incredible.
That wide field capability is literally the only reason we caught this 7-year shutdown in J0218.
Because if you only look at a galaxy once a century, you will miss these rapid, fleeting phase changes entirely.
You never even know they happened.
Which raises a massive question.
Go on.
What if J0210 isn't a freak accident? What if, as these wide-field surveys continuously monitor the sky over the next few years, we start finding dozens or hundreds of these rapidly starving supermassive black holes?
If this rapid shutdown is found to be a common occurrence, it fundamentally alters our understanding of galaxy evolution as a whole.
Because it would suggest that supermassive black holes don't just slowly, steadily burn through their fuel over eons.
Right. It would mean they gorge themselves, abruptly and violently shut down, and then perhaps restart again in these cyclical cosmic hiccups.
And because the black hole is the engine right at the center of the galaxy, its behavior dictates the environment of the entire galaxy around it.
Exactly. It's connected to everything. The extreme radiation from an active AGN heats up the gas in the surrounding galaxy.
And hot gas can't form stars, right?
Right. It actually prevents new stars from forming. It essentially sterilizes the galaxy.
Okay.
But if a black hole can suddenly shut off its energy output in just 7 years, it drastically immediately changes the thermal environment of the host galaxy.
The gas cools down.
Yes. And that can potentially trigger sudden massive bursts of new star formation.
Yeah.
So the life cycle of the central black hole is intimately tied to the life cycle of every single star system around it.
It's all connected. It really paints a picture of a universe that is, breathing, flickering, surging, and starving all the time right over our heads.
It's far more alive than we give it credit for.
Think about your own perception of the night sky for a second. We use the stars as these ultimate symbols of eternity and permanence.
We do.
We just assume the cosmos is this quiet, ancient backdrop to our super fast-paced human lives. But the evidence from J0208 clearly shows that the universe is just as restless, unpredictable, and capable of sudden, shocking transformations as absolutely anything here on Earth.
It is a highly active, turbulent landscape. And we are really only just now building the observational infrastructure capable of watching that turbulence unfold in real time.
We're finally opening our eyes.
Every new anomaly we find forces us to look deeper and refine our understanding of the extreme physics governing the dark.
Which leaves us with a truly mind-bending final thought for you to ponder tonight.
Let's hear it.
The light from the starving black hole took 10 billion years to cross the void and reach our telescopes, delivering a message of sudden, catastrophic change that happened long before our planet even existed.
Long before.
So when you look up at that seemingly quiet sky tonight, ask yourself this: what other invisible cosmic alarms are going off right now?
That's a chilling thought.
What massive instantaneous transformations in the very fabric of the universe are rushing toward Earth at the speed of light right now, carrying the news of a radically altered cosmos?
News that our descendants won't actually see for another billion years.
Exactly.
The universe is constantly broadcasting its evolution. We just have to keep our instruments calibrated, our minds open, and, well, be willing to throw away the rule book when the light finally arrives.